Chem 201, College Chemistry 1, Chapter 8. Chapter 8 is Bonding General Concepts. Here for this particular chapter, we will be studying how atoms bind together, right? So they form these forces, which we call chemical bond. We will see the type of chemical bonds that are formed in chemistry. The most important, as we will see later on, will be the Ionic and covalent. We will see that electronegativity, which is another periodic trend, which was not seen on chapter 7, but we will see that also electronegativity has like a big contribution to chemical bonding. So here are the consequences of electronegativity, bond polarity, and dipole moments. We will see ionic. This is where ionic size will come in, but we saw it already on chapter 7. So we'll just brush up a little bit and maybe just skip it past it because you can see that it's a pretty long chapter. So energy effects in binary ionic compounds, that is the lattice energy. In the book, you will see that lattice energy is a big section, but we are skipping that part of lattice energy. Lattice energy is about the energy that keeps a crystal together in an ionic compound. Okay, ionic characters in covalent compounds. That's part of the electronegativity and the polarity. So we will see the models for some chemical reactions. For some compounds, we will see like what shape a particular molecule has, what is the angle, what is the geometry. We will see how are the electrons distributed. We will see the Lewis structure, very important, very critical, mostly for the ones that are taking organic chemistry and inorganic in later on, and really to represent any molecule. Because some of you might say like, why do they angle this compound? Let's say like carbon dioxide, right? So let's say carbon dioxide, you normally see the drawing like this shape is linear. This is carbon dioxide, CO2. Why is it that carbon dioxide is not drawn in a L shape, let's say, right? So C double O and C double O. Why is it like this is wrong? What makes this compound here wrong versus this one that is supposed to be the correct way how to draw a carbon dioxide? What are the differences between the shapes? Why am I allowed to do linear? Why am I allowed to do some bending? Exceptions of the octet rule, that's a consequence. I mean, that's part of the Lewis structure, resonance, and then the valence shell electron pair repulsion model. That's another way how to you will use it to represent in a 3D version all the molecules that we will study now. Okay, so the questions to consider for this chapter, I mean, that's how we're going to start this chapter, is by formulating this question: what is meant by a chemical bond? When do we form a chemical bond? Why do atoms bond with each other to form compounds? How do atoms bond with each other to form how do they do it, and why do they do it, right? So those are the ones that are going to be answering today in this very first part of the chapter. So what is a chemical bond? A chemical bond really is a force, okay? So you might think that, oh, there is really like is it really, let's say like, are they like hooks that are tying the electrons together? No, there is really not a physical hook. It is really what we have in a compound or atoms. What it is forces. So you have an ampere electron. One element will have one ampere electron, and another element has another ampere electron. Those ampere electrons, they want to get paired. So the attraction between these two ampere electrons will make that possible, a chemical bond. So that attraction is what we call a force. Okay? So there is really no physical bridge or anything between the atoms. So all what they have is forces that are holding these groups of atoms. It can be groups of atoms, it can be one single atom. Okay? So they hold them together and make them function as a unit, so forming a compound, right? A bond will form if the energy of the aggregate is lower than the one of the separated forms. Yeah, obviously, right? So if by forming a chemical bond, right, I'm going to gain energy, I will do it. But if I form a chemical bond to waste energy, I won't do it. And so that's the difference between how do I know that this atom binds to this, right? Is forming a chemical bond with this other atom. Well, you know that because of the energy. If the energy is favorable, right? So if the process is favorable, definitely it's going to form the chemical bond. If it's not favorable, then it will not do it. It won't waste money. money or energy. In this case, for chemical bonds, for elements, would be energy that, and elements never waste energy to form a chemical bond. Okay, so this is what happens. For example, hydrogen atoms. So here you have the first hydrogen atom here on the left, and then you have another hydrogen atom on the right. So you have in the center, you have the nucleus that has a positive charge, and then you have the electron cloud, right? The electron cloud is the possibility in which the electron can be circulating. So you have one ampere electron here. Let's say that it is located right there. And we have another ampere electron located right here. Why am I drawing it one spin up, one spin down? That doesn't matter. Remember, it's a 50-50 possibility that the electrons are plus 1/2 or minus 1/2, right? So then these two electrons, they notice that they are ampere. Ampere electrons are not, are not stable. Okay? So because there is an electron-electron repulsion, but every element, as we will see later, according to the octet rule, says that the electrons, they tend to have all the last shell, or at least the p shell, the p subshell, the sublevel, the p sublevel filled. So in the case of hydrogen, it's not big enough to have a p orbital, but in the case of the s orbital, it needs to have the last shell of electron filled. So that's what we are trying. I'm gonna close right now, I'm gonna stop sharing. So what I'm trying to say is that normally the atoms, they aim to be as a noble gas, right? So remember that we were saying at some point that the elements, the most stable elements of the periodic table are the noble gases. That means that all the elements, they tend to be as a noble gas. You might wonder, why is it the periodic table ending right on helium, right? So why is not continuing? Why don't we have hydrogen, helium, lithium, right? Why do we have to go back? Well, there is a reason why the periodic table ends right here. It's because these elements are the most stable. So every single element tends to reach the electron configuration of the noble gas that is on the row, right? So for example, in this case, hydrogen aims to be like helium. Fluorine aims to be like neon. Boron aims to be like neon. Carbon aims to be like neon. All these guys, they aim to be like the noble gas. For example, phosphorus wants to be like argon. Selenium wants to be like krypton. Iodine wants to be like xenon. So they will do whatever they can to adopt the electron configuration of noble gases. Why? Because noble gases are stable, are highly stable, because they have all their p subshell filled. Okay, so what happened with these guys? Lithium, you think that potassium wants to go all the way to be krypton? No, for potassium is too far to be like krypton. So what is easier for potassium? For potassium is easier to back one position. So to be like who? To be like argon. Same thing for calcium. Calcium is too far for calcium to be like krypton. So it's easier for calcium so to just go back. Go back to who? To the previous noble gas. Okay, so that is why these elements are metals. They like to lose electrons. By losing electrons, they adopt the electron configuration of the previous noble gas. These guys, on the other hand, they are non-metals. They actually like to gain electrons. Why? Because if they gain electrons, for example, arsenic, if arsenic gains 3 electrons, it will become krypton. If it loses 3 electrons, it becomes zinc. There is no gain becoming zinc, right? So that's why these elements are called the non-metals, because they aim to gain electrons to become noble gases. These elements, on the other hand, they don't. It's too far for them to get to become krypton. So instead of becoming krypton, what they will do, potassium and calcium, they will become argon by losing electrons. Okay, so that is what we have from the electron. In this case, for hydrogen, hydrogen wants to be like neon, like helium, right? Because helium is the immediate normal gas, right? The one that is, helium is element 2 and hydrogen is element 1. So definitely for helium, for hydrogen, it wants to be like helium, which is the closest noble gas. So in this case, you will have that the two hydrogen atoms, they will get closer. there is obviously there is an optimum distance, so the atoms cannot just overlap one on top of the other. So they get together and they form a chemical bond. What happened with the electrons? The electrons should be shared right here. In this case, it's not an ionic compound. For hydrogen, it's a covalent compound. Don't worry about the terms right now. I'm just telling you that hydrogen, these two hydrogen atoms are sharing the electrons. So those two electrons are going to be right in between the two nuclei. Okay, there is an optimum distance, and that optimum distance is provided by an equation. This is the there's a potential diagram, right? So what is the optimum distance? Right? So here is the internuclear distance. So in the case of hydrogen, they cannot be too close, because if they are too close, there is a nucleus repulsion, right? Because they have positive charge. So they cannot be that close. So as there is a separation, there is a minimum energy. Apparently for hydrogen, the separation or the bond length, what we call, is 0.074 nanometers, right? So that's the bond length. So obviously that's going to be different. This is for hydrogen. For lead, most likely it's going to be larger, because lead is a bigger atom. Lead, let's say when it forms a covalent bond, well, lead is a metal. So let's say iodine. Iodine is huge, right? So it's a huge element, has an atomic number 53. So iodine definitely will have a larger bond length because of the size. It's really because of the size. The larger is the atom, of course, the bond length is also going to be larger. Okay. Oh, what happens with the distance? I mean, what happens now when they are too far? When they are too far, now there is no attraction, right? So you're putting the two electrons too far, that there is no attraction. The spin plus 1/2 doesn't attract with the spin minus 1/2. So you lose that attraction. Remember that the electrical field depends on distance, right? According to the Maxwell laws. So from physics, so they are too far. There is no electrical field that they compensate. Let's continue. Ionic bonding, electrons are transferred. Covalent bonding, the electrons are shared equally. Okay, so that's the difference. I mean, because right now we're with the idea that atoms, they aimed to have the last shell of electrons filled, right? Or at least the p sub level has to be filled. So they aim to be like a noble gas. Noble gases, remember that they end in P6, right? So all the noble gases, they have P6 as the last subshell. So there are two ways how you can do that. So for example, in the case of metals, they do it by losing electrons. So electrons are transferred. So the same electrons that I need to become, let's say, so let me see here. Right? So this is the periodic table. For lithium, the same number of electrons that it takes to lithium to become helium is 1 electron, right? Because it's one step back going to helium. What about fluorine? Fluorine is one step, right? One step up to become neon. So the same number of electrons that lithium is losing is the number of electrons that fluorine needs to become neon. So what lithium and fluorine will say, like, it's okay, lithium, so you want to lose that electron. I am fluorine, I need to gain 1 electron. So why don't you give me that electron that you don't need? And then I need that electron to become neon. So that's how these two atoms will associate. So there is one case in which you can do gain and loss. That type of bonding is called ionic, because you form ions. Because fluorine now becomes F minus 1, and lithium becomes Li plus 1, right? So you form ions. And the other case is what occurs with the nonmetals. The nonmetal says, like, for example, nitrogen and oxygen, right? So nitrogen and oxygen, they also form a chemical bond, but they don't form an ionic chemical bond. Why not? Because nitrogen needs 3 electrons to go, right, to reach neon, and oxygen needs 2 electrons. So nitrogen is not going to give up. Nitrogen is not going to say, like, okay, so you, oxygen, take it. No. Nitrogen instead will say, like, I also want electrons, you want electrons. So instead of you taking my electrons or me taking your electrons, why don't we share the few electrons that we have in such a way that we both benefit from those electrons? So in covalent bond, there is no gain and loss. In covalent bond, what you have is share of electrons. So they both win. Why metals don't do that? As we said before, because lithium, all these metals, they need too many electrons to become noble gas. For example, potassium needs how many electrons? Needs 17 electrons to become krypton. It's too far. So potassium doesn't really gain anything by sharing electrons because it would need to share 17 electrons. No, it can't do that. So instead, potassium will lose the electrons. Same thing with calcium, same thing with titanium. So you will see these all tend to lose electrons, lose, because they become positively charged as all the metals. All right. So that's the difference between covalent and ionic bonds. Yep. So in one case, the electrons are transferred. That means that somebody gains, somebody loses, and the other ones are shared equally. That share equally is relative, as we will see later on. What about intermediate cases? Intermediate cases are the cases in which you don't have a full share, right? So like an equal share, or the electrons are not equally transferred. So that is what creates something in between, which is called a polar covalent bond. Okay? So from the previous slide, we have either ionic bond or covalent bond. Do we have something in between? Yes, something in between is called the polar covalent bond. So that means that the electrons are not equally shared between the atoms, right? So for example, nitrogen and oxygen, they decide to share the electrons, but then oxygen will say, I'm stronger than you. I only need 2, you need 3 to become noble gas. So since I need only 2, I am stronger, so I have more force to pull electrons. That's what creates that unequal share of the electrons. So who dictates who is stronger, right? Because we were saying that oxygen is stronger than nitrogen. How do I know that oxygen is stronger than nitrogen? Or how do I know that fluorine is stronger than carbon? Or fluorine is stronger than hydrogen? So that comes from a property which is called electronegativity, which coming on the next slide. So the unequal share of electrons results in a charge separation in the bond, okay? But I want to be very clear, it's partially positive and partially negative. It is not ionic, it's not ions. We don't have ions, right? So for example, here, if I do nitrogen and oxygen, right? So these two atoms are sharing those electrons. So because oxygen is stronger, I will do a partial positive for nitrogen, and partial positive is represented by the Greek letter delta. Looks like an S, but it is, I'll do it once I have my camera. And the partially negative, it will be for oxygen. It's a delta Greek letter. Here should be minus, my bad. Okay. Delta minus, and here is delta plus. That delta minus delta plus is totally different from saying sodium plus, okay? So don't confuse sodium plus with sodium delta plus. So for example, this Na plus, this is an ion. This is not, this is a polarized atom. Polarized atom is not the same as an ion. The ion, in this case, sodium, is a cation, has a formal charge +1. Here, nitrogen is not +1. Nitrogen is delta plus, meaning that it has some loss of electrons, but not loss enough, right? It's not the loss is not enough to become fully positive, right? So it is a delta. So that means that it's partially losing, but it has not fully lost that electron, like in the case of sodium. Okay, so that is what happens in, let's say, like the electric field when they put hydrogen fluoride. Hydrogen fluoride is HF. They share electrons. Why do they share electrons? Because hydrogen is a non-metal, and then fluorine is also a non-metal. Remember, metal and non-metal, ionic. Non-metal and non-metal is also covalent. So in this case, hydrogen is non-metal, fluorine is non-metal, therefore they form a covalent bond. So what happened with HF? I mean, you would assume, okay, covalent, that means that they share electrons. If they share electrons, that means that H and F should be neutral, right? There should be no charge. But apparently they put HF in 2 plates with electrical fields, and they noticed that some part of the molecule was oriented, let's say like hydrogen, was oriented to the negative field, right? You see here all the angles, how all the hydrogen atoms, which is the blue balls, those blue balls are oriented towards the negative plate. Whereas the green balls, which is the fluorine, or the fluoride, right? The fluorine is oriented or facing the positive plate. Why is it like that, right? At the beginning, it was randomly placed, right? Here, all the all the molecules were facing everywhere, right? But once you turn on the electricity, the electrical field, they all change their orientation. That is because of of the the polarization of the molecule. Okay, so what is it meant by the term chemical bond? The chemical bond is a force that holds two atoms together. Okay, it can be in two different ways, either by gaining or losing electrons, forming an ionic bond, or by sharing electrons, forming a covalent bond. That share can be equal and unequal. If it's equal, it's called covalent bond, or what we also say pure covalent bond. But if that share is unequal, it is called polar covalent bond. Why polar covalent bond? Because it's unequal. That means that somebody is winning slightly more than the other atom. Okay? So why do atoms bond with each other to form molecules? Because they all want to aim the electron configuration of the closest noble gas. The closest noble gas, remember, noble gases are the most stable elements in nature. So every element wants to adopt their electron configuration. So some atoms will do it by gaining electrons, some atoms will do it by losing electrons. In the case that two atoms that need to get together, then what they will do is they will share. But why do atoms bond with each other? Because that makes them more stable, because they will turn them into noble gases. Right? So the electron configuration of a noble gas. How do atoms bond with each other? Yeah, we said that by either losing and gaining, or by sharing electrons. And so we answered the very first part of the of this slide, right? The questions. Electronegativity, that's the property I was telling you. How do I know? How can I predict which one gets the delta plus, which one gets the delta minus? So electronegativity is defined as the ability, it's a property, okay? So it's the ability of an atom in a molecule to attract share electrons to itself. So that means that if I have electrons nearby me, then if I'm electronegative, then I will be able to to drag those electrons closer to me. Right? For a molecule HX, the relative electronegativities of the H and X are determined by comparing the measures of the bond energy. And so there is a scale. Well, here in electronegativity is a periodic trend, and then increases across a periodic the period and decreases down the group. So what it will be, it is I think the next slide here is by numbers. I mean, they have a numerical value. We don't have to memorize that, obviously. But for example, you can see that fluorine is the most electronegative element of the periodic table with a value of 4. And the least electronegative or more electropositive is cesium, and francium. Okay? So cesium and francium, they have an electronegativity of 0.7. That means that they don't like to gain electrons at all. This is the periodic table. And then this is the electronegativity values. Once again, you don't have to memorize that. It's a periodic trend. So the electronegativity, I would say, increases from left to right, and also increases from bottom to top. Right? It's a periodic trend. That's how the electronegativity increases. So fluorine is your most electronegative element with 4, and the weakest is francium and cesium. Normally we ignore francium because, as I said before in some other lectures, francium is a radioactive element, so we don't really count it. So the natural and the stable elements, right, that is on the far left and bottom, it would be the cesium. Cesium is your most stable compound. Francium is radioactive. Same thing with radium, right? Radium is also an alkaline earth metal, but normally you don't count radium because it is radioactive. Barium is normally uh, is the one that is the last alkaline earth metal element. Same thing for alkali metals. Cesium is supposed to be the most stable, the one that we normally mention as the most metallic compound. Right? So that would be the trend, and then that's how you're going to organize the elements based on electronegativity. Concept check. If lithium and fluorine react, which one has a more attraction for electron? Well, fluorine, right? Because if you look at the periodic table, fluorine, let me draw more or less the periodic table here. Right. This is an ugly periodic table, but this is my periodic table. So lithium is more or less here, and fluorine is all the way here. Right? So according to the electronegativity increases from left to right and from bottom to top. So lithium and fluorine, so fluorine is all the way on the right side. Therefore, fluorine should be has more attraction for electrons, right? In a bond between fluorine and iodine, which one has more attraction for electron? Well, iodine is right here, it's at the bottom. So here we're really not debating between left or right, because here they're all on the far right of the periodic table. But iodine is lower than fluorine. So remember, the electronegativity increases from bottom to top, meaning that fluorine is also the most electronegative, so has a higher attraction for an electron. Okay, so this is more or less what is the relative electronegativity differences to form different type of bonds, right? So if the electronegativity difference is very large, then you are in front of an ionic bond. If it's an intermediate, then you have a polar covalent, and then you have zero or close to zero, you will have a covalent bond. Okay, so that means that I have to memorize all that table? No. So in this case, I think that by numbers, 1.9, at least is 1.9 difference. That's the minimum to be an ionic compound. So for example, if you have fluorine and cesium, for example, that would be your most ionic compound that you form. The difference in electronegativity would be 4 minus 0.7. That is 3.3, right? The minimum is 1.9. So 3.3 is super ionic, right? Because it's the most ionic. What if I form a compound between, let's say, lithium, or let's do something else, calcium, okay, and chlorine? Is this ionic? Yes, because chlorine is 3 versus calcium 1. 3 minus 1, 2. And the minimum to be ionic is 1.9. So calcium chloride should be ionic, right? So the 1.9, and then for the other, for covalent, I think it's 0.4 is the boundary, meaning that for example, CH is supposed to be covalent. No? So 0.5. 0.5, I would say 0.5 is the boundary between polar covalent and covalent, and the boundary or the limit between polar covalent and ionic would be 1.9. Right? So that would be the domain differences. So here you will have ionic compounds after 1.9. Between 0.5 and 1.9, it would be polar covalent. And below 0.5 would be pure covalent, right? Covalent bond. And so we can use that as a reference. But again, we don't need to memorize the electronegativity. Normally we do it by reference. Reference in terms like by looking at the periodic table, and we'll say, oh, this is ionic, this is polar covalent, this is covalent. Exercise, arrange the following bonds to least polar. Most to least polar, right? So we have nitrogen fluoride. Let me write it on this piece of paper. I will do one of them, because again, I will do, let me do at least two. OF, NO, BCl. Just in case I write the last one. Okay, so what do we have in here? So they arrange the most polar to the least polar, right? So that's what they want us to do for this particular problem. So here, definitely I have to use the periodic table. NF has a difference of 2, right? I'm using the periodic table, not the values of electronegativity. So NF and CF, which one is more polar? Definitely CF is more polar, right? Because the difference between carbon and fluorine is 1 to 3 elements away, whereas nitrogen fluorine is 2 elements away. Okay. What about CL? Well, Cl and Cl, they have the same strength. They have basically the same electronegativity. So there is no electronegativity difference. So which one would be more polar? Well, would be more polar, it would be CF, followed by NF, followed by Cl. Okay? So that would be my trend for this particular group. In this other group, so I have oxygen, fluorine. They are right next to each other. Nitrogen, oxygen, they are also next to each other. Boron, chlorine, right? So that would be my most polar, I would say. Right? Boron, chlorine is my most polar because there's a huge difference. Nitrogen, oxygen, and oxygen, fluorine, these are the closest, right? They're very close, but fluorine, remember, is one step away, but the advantage is that fluorine is super electronegative, right? It's the most electronegative. So I would say that the most polar would be BCl, right? Because that's the, then followed by OF, followed by NO. I mean, I'm sure that they did it by the numbers. I mean, that in this case, you will need the numbers to see what is the exact, because here it's only one step away, one step away. It will have to be, but that's my guess from the periodic table. Let's see how is this guess aligning with the values, right? The numerical values. Let's see now, carbon, fluorine is three steps away, right? Silicon, fluorine, but silicon is less electronegative than carbon. So it would be 1, 2, 3, 4, 4 steps away, right? 4 steps away, why? Because 1, 2, 3, 4, or 1, 2, 3, 4 to get to fluorine. And sulfur, chlorine is just right next to each other. So this one will be the least polar because it's only one step. So this one has carbon, fluorine would be the my most polar would be silicon, fluorine, followed by carbon, fluorine, and then followed by sulfur, chlorine, right? Because it's only one step away. Okay, so let's see how this from periodic table compares to the results by using values. So the first one, I have CF, yes, that's my most electronegative. Then NF. Oh, here, I don't know where they get NF. I guess this is a typo. Okay, my bad. I should have checked before. Apparently, this is not oxygen. Apparently, this one is fluorine, which would change definitely the trend, right? So, yeah, if it's NF, yeah, that is gonna make it the most polar because of the difference between nitrogen and and fluorine. After that is SIF. Oh no, my bad. So here we're looking at it. This one, the A, yeah, that one matches. NF, OF, yeah, CF in my first one. Next is NF, right? This one is for A. I'm misunderstanding the answer. CF, right? We got it right. NF, we got it right. And OF. OF. What is OF? Okay, here. Oh, they did it vertically. Oh, my bad, my bad. Yeah, I did it incorrectly. Because here it was supposed to be, the trends were supposed to be this way, and I did it vertically. Okay, so let's let's explain the answer. I mean, let's explain here. The largest difference in electronegativity is CF, right? CF is right here, followed by NF, right? Because it's only 2 steps away according to periodic table, and OF is only 1 element difference, right? In distance from the fluorine. The next one is silicon fluoride. Yes, silicon fluoride. Yeah, that was in our trend, right? So it's the most polar. Then I would say it's carbon. Yeah, CF should be the next one because it's only 3 steps away from fluorine. Silicon is 4 steps away from fluorine. And nitrogen and oxygen, these are right next to each other. So it's only 1 step away. So before I open the last one, so the most polar should be boron chloride, right? If we look at the C trend. Because the distance between boron and chlorine, if you look at the periodic table, it would be like 1, 2, 3, 4, 4, 1, 2, 3, 4, 5, five elements difference. Sulfur chloride is right next to chlorine, and then chlorine is polar. So it would be BCl, SCl, and ClCl, right? Sorry for the misunderstanding. I was thinking that they want us to rank vertically, but it was organizing it horizontally. Okay? But again, what we have to do is really look at the trends based on the um, based on the separations, right, between the two elements that you are discussing. What is dipole moment? Dipole moment is also a property. It is not the same as electronegativity. Some people confuse polarity, bond polarity, with dipole moment. It's totally different. I mean, they are related, but they are not the same thing. Okay, so dipole moment is a property of a molecule whose charge distribution can be represented by a center of positive and negative charge, and a center of positive charge and negative charge. Use an arrow to represent a dipole moment. Point to the negative charge center. Okay, so what we do here is, I'll explain that here. The difference between electronegativity or bond polarity. Bond polarity comes, for example, in our example that we had here, right? BCl, let's say BCl. Right? So we said that chlorine is more electronegative than boron. Therefore, this one, I will put a delta minus and delta plus. Okay? So because boron is less electronegative than chlorine. So the net charge, right, or the electrical field, it will go towards this side. Right? So the dipole moment is of this bond, it goes this way. Always goes towards the delta minus. If I look at OH, right? In this case, oxygen is more electronegative than hydrogen. So it would be delta minus for oxygen and delta plus for hydrogen. So, and then the dipole moment will be drawn like this. But this is only based on bond polarity. What happens if I have BCl3, which is a molecule? So then here, what I have to take into account is every single bond. This is the difference between bond polarity and dipole moment. I have to take an average of everything. So in this case, delta minus, delta minus, delta minus, delta plus, right? How are the electrical fields? From delta plus to delta minus, one pole here. From delta plus to delta minus, one pole. Then from delta plus to delta minus. So I have three dipole moments. One going up, one going right to the bottom left, bottom right. So I have to take an average, or what we call, for the ones that are taking physics or have taken physics, vectorial analysis. These are vectors. So you have to do vectorial analysis to determine the actual value. But we don't do that in chemistry, okay? So in a general chemistry course, we don't get the vector, we don't do the vector analysis. What we only do is, do they cancel out or not cancel out, or do not cancel out? Okay, that's all what we care. Do you think that these arrows will cancel out? No. In what case cancels out? If you have something up and something down, they will cancel out. Okay, so if you have something that cancels out, that means that the dipole moment is equal to 0. That's the abbreviation for dipole moment. Dipole moment is the mu Greek letter is dipole moment. The mu equal to 0, that means cancel out. What does that mean that the dipole moment is 0? That means that the molecule is non-polar. What happens if they do not cancel out? Then we say that the dipole moment is different from 0. That means that the molecule is polar. Okay? It's different saying that the bond is polar versus the molecule is polar. If you say that the molecule is polar, you have, that is the assumption that you have done a vectorial analysis to see if the internal polarities cancel out, right? So in the case of water, what happens in water? Well, in water, we know that water is very polar. This is the molecule of water. We have delta minus, right? Delta plus, polarity towards the oxygen, right? We're talking about polarity, bond polarity here. What happened with the electrons? The electrons also have a polarity, is towards to the upper part. Don't worry about this. We will do more on this later. But the polarity of oxygen, up, up, up. So how are the fields, right? Up, up, up. Do you think these guys cancel out? No. So if they don't cancel out, that means that dipole moment is different from 0. If it's different from 0, the molecule is polar. So that's why water is a polar molecule. Okay? Carbon dioxide, another example. Carbon dioxide, this is the drawing of carbon dioxide. Oxygen is more electronegative than carbon. Delta minus, delta minus, delta plus. How are the fields or the vectors? The vectors are always from delta plus to delta minus. Arrow this way, arrow this way. Do they cancel out? In this case, they do cancel out. So dipole moment is equal to 0. Therefore, the molecule is non-polar. Okay. Can I cancel out anything that is opposite? Yes, you can cancel out anything that is opposite only if it's the same. For example, COO cancels out with another COO. What happens if I have COO, COS, right? Sorry, C sulfur, right? Carbon with sulfur. Yes, I also have delta minus, delta minus, delta plus. This vector this way, this vector this way. Can I cancel this out? They are opposite. No, I cannot cancel these two. Why? Because this one is a COO left and this one is a COS right. They cannot cancel out. Here they do cancel out because this is COO left, COO right. So they are equally the same. That's why I can cancel them out. But here I can cancel them out. So here I will have delta is different from 0. So you will have that this one, you will have to label it as a polar compound. Of course, there are some other rankings, right? Because it's not like that, it's not day and night, so it's polar, non-polar. No, you can have a molecule that is like a slightly polar. You can have something that has medium polar and also strongly polar. Those details of polarity are studied more in depth in organic chemistry. For the ones that are taking organic chemistry 1, definitely we will go over that polarity. So it's not polar. So here you will have a slightly polar, you have medium polarity and a high polarity. So you will have even subdivision. So what will be the ranking for this one? Here we will have a small polarity, very small polarity, more towards the non-polar side. Why? Because the polarities are very similar, even though they don't cancel out. But numerically speaking, right, the value is very close because it's oxygen and sulfur. They're very similar elements. I mean, based on the electronegativity. So there will be some more on the non-polar side, but they are polar. There is a small polarity in this particular compound, okay? So right now, my purpose was just showing you what is dipole moment. Dipole moment really takes into account every single polarity, and then you do an average, right? Well, we say that an average, but it's really a vectorial analysis. We don't do the formal vectorial analysis. All what we want to know if they cancel out. If they cancel out, the dipole moment is equal to 0, non-polar. If they do not cancel out, then the dipole moment is different from 0, the molecule is polar. That's what all we care right now. Polar or non-polar. Do they cancel out or they do not cancel out, right? So let's continue now with these slides. This is for water. For example, you see water delta plus for hydrogen here, and then another delta plus. Here you will have a vector going this way towards oxygen and another vector going here towards oxygen. And of course, here you have the electrons going this way. If you do an average, for example, here they did the vector analysis. They combined these three vectors, and then the result was this horizontal vector. So that's why water is highly polar. How do I know this? This is an electron density map. Anything that has a red area, that means that it is electron rich. Right? If you see something that is blue, that means that it's electron poor. So that means that in this particular molecule of water, all the electrons are concentrated on the oxygen. And the part of the water or the hydrogen is weak in electrons, in electron density. Once again, it's not that it is not shedding electrons. They're shedding electrons. It's only that hydrogen is partially deep protected. Okay, so let's continue with the dipole moment, right? That's exactly the net dipole moment when they cancel out, right? The dipoles cancel. So in this case, they have also the example of carbon dioxide. They have that the two dipoles go to one side to the other side, they cancel out. So you will have that the molecule is polar, non-polar, because you have the charges equally distributed to the left, equally distributed to the right. So the charges cancel out, the molecule is non-polar. Stable compounds, right? So atoms are stable and have a noble gas electron configuration. That's really the driving force, that atoms in a stable, they want to be as a noble gas, the closest noble gas. Right? when two metals react, they form a covalent bond, right? We mentioned that before, and then they share electrons. When a non-metal and a metal react, they form a binary ionic compound, right? There is a loss and gain of electrons. And then who are the ones that do that? I mean, who are the ones that are responsible for that losing and gaining electrons or sharing electrons? Those are the valence electron, right? On chapter 7, we were saying that the valence electrons are the electrons that are located on the outermost shell, the last shell of electrons in the electron configuration. Those are the valence electrons. So those are the first ones that are going to be facing the other element, either if the other element wants to attack or the other element wants to share, right? So in an ionic compound, right? So it's any compound that conducts an electrical current when melted will be classified as ionic. Yeah. The models are attempts to represent how the molecule looks like, right? So whenever we say models now at this point, we're trying to really say like, how do we think that the molecule looks like in the atomic or molecular level? Obviously, nobody has seen a water molecule. It's too small. We're talking about the 10 to the minus 10, 10 to the minus 9 meters size. It's too small. There is no microscope that is able to watch or to see a water molecule. The biggest we have, I mean, the smallest we have seen is DNA. We are able to see DNA, but DNA is thousands larger than water molecule. So it's impossible for us to see water molecule. We cannot see water molecule. We cannot see carbon dioxide. We cannot see even hydrogen peroxide. So what should we do with those molecules? Well, we just predicted, so that's why these models were created. Okay. Fundamentals of the models does not equal reality because nobody has seen it, right? So they are oversimplified and they are often wrong. Yeah, definitely. Well, similar to the models that are in the fashion shows anyway. Models become more complicated and are modified with as they age. Yes, because every model, the models are evolving. For example, if there is a new study that say like, oh, fluorine is not as electronegative as it was thought it would be. Well, then the model changes. Right? So we must understand that there are many assumptions. So when a model is wrong, we learn as much as we can, so to not make the same mistake with the other models. Bond energy, also we want to know, since we're forming a chemical bond, we want to know how much does it cost, right? So, okay, so I have a hydrogen, bonds to hydrogen, but how much energy does it gain? Because we were saying that bonds will only form a chemical bond, sorry, elements will only form a chemical bond if they become more stable or the attachment is favorable. How much energy do you gain? Well, the bonds, to form bonds, energy is released. So normally forming bonds is exothermic, but breaking bonds is endothermic. So that means that you have to invest to break a bond. So this is a formula that we will use a lot. You also will use this in organic chemistry 1. I used to teach it, so I know that we do this type of problems. So enthalpy of a reaction is equal to the summatorial of all the bonds that are broken minus the energy of all the bonds that are formed. Okay? So it's the bond energy that per mole, and it always has a positive sign. So here we have an example. So here we have, what is that? CH3, C triple N, right? Sorry, N triple C. Yeah, it's not the same thing, N triple. Okay, look at the bond energy. CH cost me 413. C single N cost me 305. C single C cost me 347. C triple N cost me 891, right? So that's the bond energy, delta H bond energy. Okay, so they want me to know like what is the energy associated with this process, right? So this is acetonitrile, and this one is isonitrile, I think, methyl isonitrile. Well, all right, so here we have to see what we're breaking, what we're forming. CH3, CH3, they're exactly the same. I'm not breaking, I'm not forming anything. but here I have a bond. Here is a bond carbon-nitrogen. Right? Oh, but it looks like hydrogen-nitrogen, yes, but it is, we will do that in a second, but really this is like this, carbon, hydrogen, carbon, hydrogen, this is the same thing. Maybe I should write it as it is. Okay, so here really the bond is CN, so CH, 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 nothing is broken, nothing is formed. CN, I don't see that CN anymore. So I'm breaking CN, right? Here, forming CC, right? That's the difference between the two sides. Breaking CN, forming CC. N triple C, C triple N is the same thing, right? C triple N, C triple N, right? So it's the same thing. So the only thing that I'm breaking is CN. The only thing I'm forming is CC. So according to the enthalpy, to be equal to the energy, that is the breaking, right? Because these are all positive. So how much of breaking is going to be positive energy, bond energy of breaking, minus bond energy of forming, right? Of bonds that are being formed. So P of breaking, what am I breaking? I'm breaking C triple N, 305, right? Minus, what am I forming? I'm forming C triple C, 347. So what is the difference between this? Should be 42, right? So minus 42 kilojoules per mole. So this is a favorable process, for example, because it's exothermic. Okay, so let's see what the answer says. Minus 42 kilojoules per mole. Yeah, definitely. Okay. Okay, let's continue. Localization, electron model. A molecule is composed of atoms. Now we will start putting atoms together. Okay. They use the orbitals. Electron pairs are assumed to be localized on a particular atom or in the space between the two atoms. Yeah, that's what we do when we form a bond. Like, for example, in my example, I was drawing the CHs and the CN, the C triple C. So those are the spaces between the atoms. Normally, they do it by overlapping the orbitals. Remember, we were saying that we have orbitals S, P, D, F. Well, the orbital P that is partially filled in an atom, it will overlap with the orbital that is also partially filled of another atom. So they overlap and they form what we call a chemical bond, which is in this case covalent, right? If we're talking about two nonmetals. So if you have electron pairs, well, they are supposed to be localized on a particular atom or in the space between the two atoms, right? So if they decide to form a chemical bond, so there will be a space between the two atoms where the electron will be located. If the atom does not want to form a chemical bond, it will be localized on the atom. It will not go anywhere. Lone pairs are pairs of electrons localized on the atom, and the ones that are in the space are bonding pairs, right? So that's the difference. The localized in the atom are called lone pairs, and the ones that are in the space between the two atoms, those are called the bonding pairs. Description of the valence electron arrangement, Lewis structure, that's what we're going to do right now, how to represent an atom based on the valence electrons. We'll predict the geometry using the valence shell electron pair repulsion, known also as the VSEPR model. Yep. So, and then the description of atomic orbital type used to share electrons or hold lone pairs. So we will see how an atom, or sorry, how a molecule can be drawn or represented. Lewis structure shows how valence electrons are arranged among atoms in a molecule. And so reflects the central idea, the stability always tries to reach the noble gas electron configuration. So Lewis is a scientist, that's the last name of the scientist. He is the one that came up with this type of representation of the atom. Okay? So it's very useful to explain chemical bonding, and also how the stability is reached, right, to achieve that noble gas electron configuration. So this is the dual rule. That only applies to hydrogen and helium because those are the smallest atoms on the periodic table. So hydrogen, helium is the noble gas. So they only want the dual rule. That means that they only tend to have 2 electrons in the last shell of the electron configuration. The octet rule, which is the most popular and the one that applies for most of us, for most of our elements. So the octet rule says that the elements try to be surrounded by 8 electrons. In the case of fluorine, tries to get surrounded by 8 electrons. Okay, so how do I do that representation? Okay, so let's go now to Lewis structure. In Lewis structure, what we are going to see is, let's say, I want to write the Lewis representation of nitrogen. Let's say nitrogen. Good. Okay. Nitrogen. What is the number of valence electrons of nitrogen? We said that valence electrons is given by the groups, right? The group number. So if nitrogen is under group 5A, that means that nitrogen has 5 valence electrons. How do I draw those 5 valence electrons? According to Lewis, he says 1, 2, 3, 4, and 5. Okay, you always have to do one at a time. Can I do nitrogen 1, 2, 3, 1, 2? No, that's wrong. You can't do this. Oh, can I start? You started from the top. Can I start from the bottom? 1, 2, 3, 4, 5. Yes, this is correct. Doesn't matter where you start. As long as you go one round, and if you have extra, then you can continue, right? But you cannot do that. Do 1, 2, 3, 4, 5. This is wrong. It's 5 valence electrons. No. Okay. Or can I do like 1, 2, 1, 2 like this? No. Also, that is wrong because you left this face empty. It has to be completing the 5 phases. 1, 2, 3, 4, and 5. Okay. Only 4 phases has to be completed before going to the second pairing, right? I mean, to the pairing of electrons. Another one, let's do bromine. If you go to bromine, according to the periodic table, belongs to group 7A of the periodic table. That means that it has 7 valence electrons. So for bromine, I will have to do 1, 2, 3, 4. Then I start pairing 5, 6, and 7. Okay? So that will be the Lewis representation for bromine. And then you can tell that if this bromine helps you to determine how many bonds it can form. In the case of bromine, how many ampere electrons it has? It has 3 ampere electrons. That is telling you that nitrogen is able to form 3 covalent bonds. You see? Because that gives you room for 3. What about bromine? Bromine has already 3 lone pairs. What about that one? That one is 1 room, has a possibility to form a bond here. The ampere electrons are the ones that are able to form the chemical bonds. In the case of oxygen, oxygen has 6 valence electrons. 1, 2, 3, 4, 5, and 6. That means that oxygen can form two bonds. Okay? So each of these can form a chemical bond. So why is it forming a chemical bond? Because if it forms a chemical bond, it gets the octet. Why? Because here I'm going to count down the number of electrons, right? So far you have 1, 2, 3, 4, 5, 6. But here, theoretically, is sharing electrons with somebody else. Here is sharing electrons with somebody else. Since they are sharing electrons, that means that these electrons belong also to oxygen. Oh, but it belongs to element X. Yes, they also belong to element X. But since they are sharing, these 2 electrons belong to oxygen, and these 2 electrons also belong to this element X. So in this case, oxygen has 1, 2, 3, 4, 5, 6, but 7 and 8. So by forming that, oxygen has now 8 valence electrons. Does it formally have the 8? No, only has formally 6. But because it's forming covalent bonds, it is still, not steals, but shares the 2 electrons from these elements. And then it will get 8. Who has 8 electrons? Well, now it will be under the electron configuration of neon. Neon has 8 valence electrons, which is the dream of oxygen. Oxygen, it dreams being neon. So to be neon, it will just do whatever it takes. So in this case, sharing electrons with X. That X can be anybody. I mean, it can be water, right? Can be H, can be any other element as long as it completes the octet, right? So let's continue with the a covalent bond. With a single covalent bond is a bond which 2 atoms share only 1 pair of electrons, but you can also have multiple bonds. Dual covalent bond, which we call a double bond. For example, oxygen. Let me form how I can form a covalent bond. So for that, I will do an example. So they tell me that hydrogen and oxygen, right, get together. Or they tell me draw the structure of hydrogen and of water. So I have oxygen, has 6 valence electrons, 1, 2, 3, 4, 5, and 6, right? And hydrogen, how many electrons hydrogen has? Hydrogen has 1 electron. Hydrogen has 1 electron because hydrogen belongs to group 1A of the periodic table. This one is 7A. Don't listen to that. So hydrogen really belongs to group 1A of the periodic table. They did it here, they put it here, not because it belongs to 7A, it's only for proximity to helium. But hydrogen really doesn't exist here. Hydrogen exists here as a 1A. So you can see that water, oxygen forms a chemical bond here, and oxygen forms a chemical bond here. So the result will be, here I'm applying geometry already, so don't worry about the geometry, but here will be the representation of water, see? Single bonded, single bonded, okay? Now, the other case, carbon dioxide. Okay? Now they tell me this is a single covalent bond, or what we call it a single bond. For carbon dioxide, we have carbon has four valence electrons, and oxygen has 6. 1, 2, 3, 4, 5, and 6. And here I will put another 1, 2, 3, 4, 5, and 6. Yeah, I'll put it here. So this one has 2 ampere electrons. Carbon goes there, carbon goes there. What about the other oxygen? The other oxygen also has 1 here and 1 here. So what is the result? Carbon COO, carbon COO. You would say, oh, why did these 2 lone pairs were down? Now you put it up. Doesn't matter. It doesn't matter where you put it, as long as you have the lone pairs of electrons showing. So here is what we call the double bond, or a double covalent bond, right? So how do I know which one goes in the center? How do I know, for example, here oxygen goes in the center? Normally you always include the element that has the highest number of ampere electrons in the center. Okay, normally. Why? Because since that one has the maximum number of ampere electrons, that means that it also has the maximum number of bonding, right? So it forms multiple bondings. So you want to have that element with multiple bondings in the center. I would never put a hydrogen in the center, for example, because hydrogen has only 1 valence electron. How can you branch out with somebody that has only 1 valence electron? No. I will branch out from carbon because carbon has four valence electrons, 4 ampere electrons. So definitely the branching of carbon is going to be really high. It has 4 possibilities. So you always include your central, that's what we call a central atom. The central atom has to be your element in the formula that has the highest number of ampere electrons, right? And a triple bond could be carbon monoxide, COO. In the case of COO, you have here there is no central atom because you have only 2 elements, right? Here you only have three elements, right? 1 oxygen, 2 carbons. But if you have 2 only, that doesn't matter. Carbon 1, 2, 3, 4, and then oxygen 1, 2, 3, 4, 5, and 6. Actually, this one is a tricky one. Yes, this is a tricky one. I don't know if that would be the best. Carbon dioxide is one of the exceptions, because here what we have, well, this one you can clearly see 1 and 2, right? But here, oxygen doesn't have any more lone ampere electron. Carbon has. Then since oxygen doesn't have that, right? So what oxygen is going to say is, okay, so carbon still needs this. So by carbon being unstable, right? Because carbon will have 2 ampere electrons. So what carbon is going to do is going to send that ampere electron to pair that electron. But then this one will create incomplete octet because it will have 2, 4, and 6. Then oxygen, what we'll do is oxygen will transfer those 2 electrons and then share them with carbon. Because oxygen doesn't lose anything because oxygen has 2, 4, 6, 8 electrons already. And now carbon has 2, 4, 6, 8 electrons. Each bar means 2 electrons, right? Because it's a chemical bond using 2 electrons. So 2, 4, 6, 8 for carbon, good. 2, 4, 6, 8 for oxygen, good. So this one satisfies the octet rule. If I leave it like I did it before, right? This one is how it was before. Before it was like this. Oxygen is happy, 2, 4, 6, 8, good. But carbon is not, 2, 4, 6. So carbon is not with the octet, oxygen is with the octet, so it's bad. So to override that effect, that's why oxygen promotes those electrons to share them with carbon. So carbon now also gets the octet. So that's how it came up. So the electron configuration for the Lewis structure for carbon dioxide would be this triple bond, triple covalent bond. Okay, so let's continue with the presentation. A triple covalent bond, yeah, nitrogen, that's the easiest. Yeah, that's a very simple. Here they are missing the lone pairs of electrons, but I mean, that's something minimum. So you have 2 and 2. To get this nitrogen triple bond, you will have to do the same thing as we did with the lone pairs of electrons, right? I mean, the Lewis structure for each nitrogen. Steps for writing Lewis structure, yeah, we already went over that, right? So how to sum the valence electron for all the atoms, use the pair of electrons, that's what we were doing right now, like number of electrons, water, yeah, we went over all those examples already. PBr3, I mean, we can try the PBr3 example. And the cyanic acid, cyanidric acid. Right? So in this case, the PBr3, if you go to the periodic table, you will find out that phosphorus has 5 valence electrons. Bromo or bromine has 3 valence electrons. So I will do bromine, sorry, 7 valence electrons. 1, 2, 3, 4, 5, 6, and 7. 1, 2, 3, 4, 5, 6, and 7, right? So phosphorus, how do I know that phosphorus has to go in the middle of the central atom? Because it has 3 valence electrons. Bromine, each they have only 1 valence electron. So this one pairs with this one pairs with this one pairs with this. The overall will be phosphorus, bromine, 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 lone pair, 3 lone pairs, 3 lone pairs each. That should be my Lewis dot structure representation of phosphorus tribromide. Cyanidric acid, HCN. Oh, I'm not gonna spoil it yet. HCN. Carbon has 4, 1, 2, 3, 4 valence electrons. Nitrogen has 5, 1, 2, 3, 4, and 5. And hydrogen has 1, right? How do I know that carbon has to go in the middle? Because it has 4 valence electrons. Nitrogen has 3 valence electrons and hydrogen has 1 valence electron. So that's how I know that carbon was in the middle. So 1 carbon here, carbon with hydrogen, and then here 1, 1, and 1. So H single, C triple, N lone pair. That would be the Lewis dot structure representation of cyanidric acid, right? So let's continue with the presentation. Right, PBr3 and cyanidric acid, excellent. Draw the Lewis structure, yeah, I mean, we can continue doing as many molecules as exist in the handbook of chemistry. So let's keep going. Draw the Lewis structure, yeah, we can do that as well. I mean, again, there will be more examples for the solve problems, right? So in the solve problems, we will have definitely more examples as usual. Exceptions in chemistry is the domain of exceptions. Exceptions of the octet rule. There are elements that they do not satisfy the octet rule, and there are some other elements that actually they break the octet rule. Okay? So boron is one of them. Boron tends to form compounds in which the has less than 8 electrons. So that means that boron doesn't need to satisfy the octet. Right? The octet rule is the rule that every element tends to have 8 electrons in the valence shell. Right? So boron doesn't need, so boron normally is very happy with having only 6 electrons. Okay? So for example, boron, in this case, this molecule is called borane, BH3. So it has only 6 electrons. Boron, you will say like, oh, but boron has only, here, boron has only 2, 4, and 6 electrons, right? So where are the 8s? Yeah, boron breaks the octet rule, so doesn't need 8 electrons. Same thing happened with beryllium. Beryllium only forms 4 valence electrons. Beryllium is also a very special element. Beryllium, even though it's an alkaline earth metal, but it doesn't really behaves as a metal. It tends to form covalent compounds. Okay? So beryllium is another exception. So if you see somewhere beryllium forming covalent compounds, it shouldn't be unusual because beryllium is a very special element. When it's necessary to exceed the octet rule for one or several third rows, so when you have higher elements, like big elements, so for example, sulfur, arsenic, these guys, they tend to expand the octet rule. For example, you will see here sulfur. Sulfur in this case has 2, 4, 6, 8, 10 valence electrons. How come you can have, right? How can you have 10 electrons? Arsenic has 2, 4, 6, 8, 10. How can these elements expand the valence electron? Well, because they belong to the third row of the periodic table. So that's what I'm gonna stop sharing right now. For example, in the first row, which is hydrogen, right? Hold on, I'm gonna get it close further. Yeah. So hydrogen, this first row, they have only 2, right? 2 electrons only. They don't satisfy the octet, they are too small. The next row, second row, they follow the octet. Lithium, beryllium, well, beryllium is the exception. Boron is the exception. Carbon, nitrogen, oxygen, fluorine, they do the octet. What about sodium, magnesium, aluminum, silicon, phosphorus? They are able to expand the octet. So for example, phosphorus expands the octet. Why can phosphorus and sulfur expand the octet? Because they are in the third row. So third row of the periodic table and below, they can expand the octet. Okay, that means that they always expand the octet? No, they can. They can expand the octet. They are not always going to expand the octet. So it shouldn't be unusual to see phosphorus maybe doing the octet, but sometimes it will expand the octet. So some elements that they have the freedom to expand or to use the octet. Why, right? Why can this element? Because these elements from 3 and below, they already have the D subshell. They have the D subshell. Even the 3, if we recall, I think I have it somewhere, still have it. The third row of the periodic table already has the D shell. So that's why having the D shell opens you the opportunity to form more bonds, because your bonds are not always going to be done through the S and the P subshells. Since now you have the D subshell, you can also do the D subshell to do more bonding. Okay, these guys from the second row, they don't have the D subshell. So that means that their bonding will only depend on the S and the P subshell. So you cannot form more than 4 bonds, right? Because remember, it's 1s orbital and 3 p orbitals. So how many bonds can you form? Only 4. 4 times 2, 8. But if you have here for the third row already has d orbitals, 1s, 3 p's, and 5 d's. So theoretically, you can form 9 bonds, right? Which is crazy. I mean, no element forms 9 bonds, but at least according to the examples that we see in this particular case, in the previous case, we had that sulfur was forming 4 bonds and had a lone pair. Arsenic was forming 5 bonds, which is 10 valence electrons. So those elements are allowed to break the octet from the third row and below. So draw the Lewis structure for each of the following molecules. I will do one of them, maybe SF6, yeah, the sulfur with the fluorine. So in that case, sulfur has 6 valence electrons, right? And fluorine has 7. 6 of them, right? It's a lot. Okay. So 1, 2, 3, 4, 5, and 6. Okay. I'm using every single electron. Even why are you breaking pair electrons already, right? Because these elements are already paired. How can you? Yes, in the case of larger elements that can break the octet, they are able to use their pair electrons to form chemical bonds. So in this case, sulfur could be sulfur hexafluoride. Okay? Well, they each have 3 lone pairs. Right? So clearly you can see that sulfur is expanding the octet, 12 valence electrons. Okay, so going back, yes, can you like these guys were already paired. How come you separate them to form chemical bonds? You can do that with these elements that are able to expand the octet, right? Let's continue. Here should be showing. Let's review. Well, really here is carbon, nitrogen, oxygen, and fluorine. They should always reach the octet, right? As we were saying, they are in level 2 on the periodic table. So level 2 on the periodic table, they never break the octet. They don't have room. They don't have the d orbitals that are used normally to break the octet. Instead, they fulfill the octet rule at 100%. Boron and beryllium, they have less than 8 electrons, and the second row never exists the octet, that's carbon, nitrogen, oxygen, fluorine. Third row and below, they are heavier elements, and they satisfy the octet rule because of the d orbitals. That's exactly what I was telling you, right? So the empty valence d orbitals are the ones that give room to expand the octet. Okay, so let's keep going. Resonance. Resonance is a really hot topic, and then it's kind of like the bottleneck for organic chemistry. For the ones taking organic 1, on chapter 2, I believe, yeah, chapter 2 of organic chemistry, you will find resonance structure. In resonance, what we do is we move electrons around, right? So why? Because remember that electrons, they have when you have multiple bonding, right? So I'll explain it like this. So you have, let's say, nitrogen and oxygen, right? So that's fine. This bond can survive because the electrons are one electron, one electron. But we already know that these electrons already have some electron repulsion. What happens if you put 2 electrons? Now you have electron, 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 electron. So what happened with these electrons? They are in a very small space. There is electron repulsion, right? Electron repulsion. What happens if you have a triple O? Even worse, because you have electron, 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 electron. The electron repulsion is really high. So what can the atom or the molecule, what can they do? So like, okay, so I know that I can form a multiple bonding, right? I can form single, double, and triple bonding, but there is repulsion. What should I do? So resonance is a property that not every molecule has that allows you to delocalize electrons. For example, in nitrate, if you do the Lewis structure of nitrate ion, this is the Lewis structure of nitrate ion. you can see here clearly that here you have a double bond, right? So the double bond is not good for any compound because it generates electronegative repulsion. So what the double bond is going to do is going to do whatever it can to move that double bond around. So how do you do that? It is basically like passing the ball. Like I have the double bond. Okay, so I will have the double bond for 1 minute, but then I will give it to you and you have it for another minute. After that, you will return it to me and then you will pass it back and forth. How do I do that? Is by delocalizing electrons. And then to do that, you need something that we call in organic chemistry, we call it conjugation. What is conjugation? Conjugation is the double bond and lone pair. That is one type of conjugation. What do we mean by conjugation? Lone pair, single bond, double bond. That's the conjugation. Or it can also be, that's another type of conjugation. Double bond, single bond, double bond. Okay? That's another type of conjugation that we have. Okay? So you have to look for that in your structure. In this case, I have the first type. I have lone pair, single bond, double bond. So what is this? What are these compounds going to do? The lone pair of electron is going to come down here to form a double bond. So since this guy is already receiving, right, this X is already receiving the electron from the left, from the right, it has to do something with the left. So it will say like, okay, now you take it. Because X is giving me electrons, so now X will give the electrons to the Y. So that's exactly what is going to happen here. Oxygen will donate the electrons to nitrogen. But nitrogen cannot take more electrons because already has the octet, 2, 4, 6, 8. If it receives these, right, it will have 10. No, it can't because nitrogen doesn't break the octet. Then nitrogen, what will do is it will say like, okay, oxygen, you take the electrons. The result, nothing happened with this one. This oxygen now will have 3 lone pairs of electrons. Right? You see nitrogen, oxygen shifted the lone pair of electrons to the nitrogen. And then nitrogen in response pushes the double bond to the oxygen. Everybody has the octet, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Everybody has the octet. You are not moving, you are not breaking the octet rule for any of the elements. Okay, so that is called the resonance. Of course, this one, all what we're going to do here is very simple. So it's only one push. In organic chemistry, definitely you will suffer a little bit more with more complex ions. Another one is carbonate. Carbonate is another ion. You can see here the conjugation, lone pair, single, double, right? You see here the conjugation. So what I'm going to do is, okay, so lone pair goes down and carbon pushes the electrons to the oxygen. This arrows is for resonance. Okay, so you move the electrons here, here, and then oxygen gets negatively charged. So what is the goal for this? Is that this double bond is bouncing. You can see how it bounces. It goes from here, and now the double bond is here. Can I do the same thing with this oxygen? Yes, you can do the same thing with this oxygen. So the double bond is not fixed in a particular space. It moves around. It goes from one center to another center. So that's how you avoid electron-electron repulsion. It's a crucial property in organic compounds. It's a key aspect that you guys have to have for organic chemistry. Most of the chemical reactions are explained through resonance, okay? So right now we're in very first step for resonance, but it's very important. Please keep that in mind, mostly for the ones that are taking organic. Yep, so this is the nitrate representation. Here there is electron-electron repulsion. You gain that, I mean, you can reduce that by pushing these electrons to the nitrogen, and then the nitrogen pushes electrons to the oxygen, right? See? Now here, I can do a second resonance structure by pushing these electrons to the nitrogen, and then pushing these electrons to the oxygen. And then I create this particular species, right? Again, so we will have, this is a keyword, delocalization. You are delocalizing. Remember, we are not allowed to move electrons. I cannot just move it from one side to the other side. One electron gets pushed, and then that push will cause another push. You cannot just push once, no. That push causes another push. So it is like a domino effect, right? Like, have you seen like those piles of dominoes that when you push one, it rolls and then it makes the other domino piece like fall, and then falls another one and then continues falling? Same thing. That domino effect, it is what we see in resonance. That one electron that gets pushed pushes the other one, and if there is a third one that can get pushed, it will get pushed, and then you will be doing that resonance in constant times, right? So here again, we are in general chemistry 1, so we are only doing one push. I mean, one pair of pushes, right? So one pushes the other, but normally it can go as many as 5, 6 pushes. Then that's something that you might see in organic chemistry. Okay, so draw the Lewis structure for the following molecules. Yeah, I mean, more example for this, we will see the solve problem part. These are bigger molecules. These are, this is the one that we did, right? We did this one already, carbon monoxide, methanol, and then oxycyanates, carbon dioxide. We will do more of these cases later on. Formal charge is used to evaluate the non-equivalent Lewis structure. So where we have to assign charges to an element, right, in a molecule. Any negative formal charge are expected to reside in the most electronegative atom. Yeah, you want to have negative atoms, electronegative atoms with negative formal charges. So, for example, if I have a bond between oxygen and carbon, who should I put the negative charge? Well, obviously to the oxygen, because oxygen is more electronegative. There is a formula for formal charges. Formal charge is equal to valence electrons of the atom minus the valence electrons, the electrons that are sitting in the atom. So I will do that in a second. Here there are some rules here. Okay, so they tell me assign the formal charges for POCl3. They show you here the Lewis structure, and I will do the formal charge. Okay. This is POCl3. They are asking me to do the formal charges for this particular representation. So in this representation, we will have to do the formula. Formal charge is equal to the number of valence electrons minus the number of electrons on the atom. That's how you're going to calculate formal charge. Let's start with chlorine. Right? This chlorine. Valence electrons of chlorine. Well, chlorine belongs to group 7A of the periodic table. Therefore, the number of valence electrons is 7. Minus, how many electrons are sitting on the atom? In this case of chlorine, I have 1, 2, 3, 4, 5, 6, and 7. Okay? So those 7 electrons are sitting on chlorine. Oh, what about this atom that is being shared with phosphorus? Yes, it's being shared with phosphorus, but it does not belong to chlorine. This electron here belongs to phosphorus. So that electron is sitting on phosphorus. It's not sitting on chlorine. So 1, 2, 3, 4, 5, 6, 7. So 7 minus 7 is equal to 0. So this chlorine has no formal charge, has 0 formal charge. The same thing will be with this chlorine and with this chlorine because it's the same thing. Let's do this oxygen. Okay. For this oxygen, you will have, what is the valence electron? The valence electron for oxygen. Oxygen belongs to group 6A of the periodic table. Therefore, the valence electron will be 6. Minus the number of electrons sitting on the atom. So in this case, for oxygen, you have 1, 2, 3, 4, 5, 6, and 7, right? Those are the 7 electrons. 6 minus 7 is equal to minus 1. So what is the formal charge of oxygen in this case? Minus 1. Formal charge of oxygen, right? Now let's do it for phosphorus. Phosphorus belongs to group 5A of the periodic table, meaning that phosphorus belongs to group has 5 valence electrons, minus the number of electrons sitting on phosphorus. Phosphorus has 1, 2, 3, and 4, right? Those are the 4 sitting on phosphorus. 5 minus 4 is equal to plus 1, right? So the formal charge of phosphorus is plus 1. So that is the formal charge for each of the elements. 0, 0, 0, plus 1 minus 1. What is the overall formal charge? 0, 0, 0, plus 1 minus 1. The formal charge is 0, right? But as it is inside, you have charges, but the overall can be negative, right? Same thing, well, we'll see some other examples. It should be plus 1 for phosphorus, right? Minus 1 for oxygen. Each chlorine is 0. Good. So here you have the same example. Which one is that's neutral? Okay. So now let's go to the molecular structure, the representation or the drawings for the molecule, right? The angles or the shape. So we will use this valence shell electron repulsion. There are some other models, but here the book uses that model for the valence shell electron pair repulsion. There are some other again, but I mean, this one is pretty consistent. So through the Lewis structure of the molecule, then count the electron pairs and arrange them, right? And arrange them in a way that minimizes repulsion. Okay? So what do we mean by that? How can I, for example, if you have to do water, right? I would never put, for example, water like this because that doesn't minimize repulsions. Right? These two hydrogens are too close. What would be the best? Well, the best, you would say like, oh, what if I spread them out? Right? But no, that doesn't happen either because you have these what are lone pairs. Lone pairs also, they have repulsion. Oh, but why don't you put the other lone pair on the bottom? Yeah, but still, the lone pair creates, lone pairs of electrons are pure electrons. So they cannot be, I mean, they will definitely angle. This one will push this way. This one will push this way. So that's why water will have to be like this. I mean, I'm putting those slopes because that's the orbital where the oxygen is, right? Having electron pairs, but it's an angle. This geometry is called bent. Okay, so there is a code. I mean, how to represent it. So, for example, carbon dioxide, right? Carbon dioxide is COO, COO. I would never think of writing carbon dioxide like that because these oxygen are too close. So the best way I can maximize the spreading is by putting them linear. Oh, but how come you did linear here and you didn't do linear in water? Because carbon doesn't have lone pairs. Oxygen has lone pairs. So those lone pairs, they create bending. No lone pairs, absence of lone pairs, they will give you expected geometries. Lone pairs, no, they distort it. They distort the expected geometry. Okay, so let's go over that. For that, you guys will have to, this one you will have to have at hand. This is a copy that I have from the book. So on the 10th edition of the book is on chapter 342 and 343. They have the geometries, right? Can be a molecule, can be linear, can be trigonal planar, tetrahedral, trigonal pyramidal, bipyramidal, octahedral. You also can have here the tetrahedral, trigonal pyramidal, V-shaped or bent, trigonal bipyramidal. You can have seesaw, T-shape, and linear. Okay? So that depends on the number of lone pairs of electrons that you have. For example, here I have no lone pairs. No lone pairs, I will get the expected geometries. But once you have lone pairs, for example, in this case, that tetrahedral is expected geometry because you don't have lone pairs, you have all atoms. Here you have a lone pair right here. So that distorts the geometry. Here you form 4 bonds, 4 electron groups. Here you also have 4 electron groups, but one of the electron groups is a lone pair of electrons. That distorts the geometry. Now you have a trigonal pyramidal. Here you have two lone pairs, like the case of water. Water is like this, right? Oxygen, hydrogen, hydrogen. But you have two lone pairs. The geometry is bent. Okay? So I would recommend you to have this at hand all times. So to determine the molecular geometry. Okay. So one is molecular geometry, and a different thing is the electron pair arrangement. Okay, electron pair arrangement, molecular geometry. Really, what we focus on is the molecular structure, molecular geometry. But the molecular geometry derives from the electron arrangement. Okay? Same thing here. 5. So the expected should be trigonal be pyramidal. But if you have 5 and one of them is a lone pair of electrons, you will have what we call a seesaw. And here 5, 2 lone pairs, D-shaped, and then 5 with 3 lone pairs, linear. Okay? So each of these is, again, it is question of memorizing or having these sheets always on your side. Okay, so we'll do more problems, definitely more practice in the solve problems videos. Determine the shape for each of the following molecules, including bond angles. So in this case, we have HCN, phosphine, and sulfur tetrafluoride, right? So in this case, we'll have HCN, we have PH3, and we have S4. Right? So in this case, I will have to draw the Lewis structure for that. I think we did this for this one. If you do the Lewis structure, you will have like that. So in this case, carbon has two electron groups. How do I know it's 2 electron groups? Because it is, the central atom has 2 electron groups, right? One is with hydrogen, another one is with nitrogen. 2 electron groups. Oh, but this one is a triple bond that counts as a single electron group? Yes. So 1 and 1, it's only 2 electron groups. No lone pairs. So for 2 electron groups, it should be, as it says here, linear. 2 electron groups, arrangement of electron pairs. They call it here arrangement of electron pairs, but I call it electron groups. 2 electron pairs, no lone pairs, right? 2 electron pairs, no lone pairs, so it's linear. Angle in linear, 180 degrees. Here it doesn't say 180 degrees, but here is 180 degrees between each 180. Integral planar is 120 degrees. Tetrahedral is 104, oh no, 109 degrees. Here it tells you, here is a combination, 120, Newtonian pyramidal, 120 here, and then 90 degrees for the perpendicular. And octahedral is 90, 90, 90, it's a perfect 90, right? So here's some angles, but the most important, linear 180, Newtonian planar 120, and tetrahedral 109 degrees, angle separation, right? So phosphine is, if you do the Lewis structure, it will be like this. So here I have 4 electron groups. What are the 4 electron groups? 1, 2, 3, 4. 4 electron groups. Or what they call electron arrangement. But one of them is 1 lone pair. Okay, so where do I have 4 electron groups, 1 lone pair? Here. 4 electron pairs or 4 electron groups. I have 4 electron groups, but then out of the 4 electron groups, I have 1 lone pair. This is the case of the 1 lone pair. You see this empty balloon? That means this is a lone pair. You have 4 electron groups, 1 lone pair. The geometry should be trigonal pyramidal. They call it trigonal pyramid, but normally, when I was a student, they call it pyramidal. It doesn't matter. Trigonal pyramid. Okay. And sulfur tetrafluoride, sulfur is 6 valence electrons. Um, sulfur tetrafluoride. And I have for this one should be, well, it depends on the is seesaw. Yeah, because of the uh, because it's 6, right? 6 valence electrons. Okay. So in this case, I have 5 groups, 5 electron groups. 5 electron groups. 1, 2, 3, 4, and 5. Right? 5 groups. So here I have in my table 8.9, 5 groups of electron pairs, and then here I have 1 lone pair. All right. So 5 electron groups with 1 lone pair right here. I have 1 lone pair. The geometry is seesaw. And the angle that it has for seesaw here should be 120, 120 in the horizontal, and the vertical should be 90 degrees. That's exactly what we have in the answer. I was looking at it because I wanted to know what is the bonding. Determine the shape for each of the following molecules, including bond angles. Okay, so in this case, let's do krypton tetrafluoride, because actually that is a good example. KrF4, okay? So in this case, we have krypton. But krypton has 2 lone pairs because it has 8 valence electrons. Remember, krypton has 8 valence electrons. Right? It's a noble gas. So yeah, now you could say also, oh, but what happened? We thought that noble gases, they never react. They are so stable. Yes. So helium, neon, argon, they are highly stable. Since these guys are heavier, they are more reactive. Remember when we were talking about discussing about reactivity, electron configuration, remember the nucleus has stronger forces with shells that are very close, right? Electrons, these electrons are tightly bonded to the nucleus, but the farther you are from the nucleus, this electron is easier to be lost. The same thing happens with the noble gases. These noble gases, for example, helium is very small. So the nucleus can retain those electrons. Neon retains electrons. Argon retains electrons. Krypton is already big. Krypton is in shell number 4. Shell number 4, you already have the F orbitals. With F orbitals, that is going to be huge, right? Because remember, F has 7 orbitals, so it's going to be huge. Xenon even bigger, right? Radon even more because it has 86 electrons already. Well, radon is radioactive anyway. So krypton and xenon, they are noble gases, but they are so big that that last electron or the shell or the valence electrons are going to be very reactive. So that's why you can form compounds with krypton and xenon. It's very unusual to see with argon, neon, and helium. Definitely no, they don't, because the atom has the electrons too close to the nucleus, so they are not reactive. So in this case, I have how many electron groups? 1, 2, 3, 4, 5, 6. 6 electron groups. And out of them, you have 2 lone pairs. So this table doesn't have that. Okay? So here, this table, you have for four electron groups, 5 electron groups. That's all. You don't have the one for 6 electron groups. But in this case, you will just have to use your creativity and also find a way how to organize this in the best. So in this case, I will have krypton. And I will have the lone pairs of electrons up and down. I have to minimize electron-electron repulsion. And the fluorines also are 90 degrees apart. So in this case, the krypton should be square, planar. Okay, so let's see what it says, the slides. It should be square planar. Ozone should be bent because ozone looks like water. Ozone is bent 120 degrees and krypton should be square planar. Yeah, 90 degrees on the plane, right? And 180 degrees between the 2 lone pairs of electrons. True or false? A molecule that has polar bonds will always be polar. If true, explain why. A polar molecule, no, not always, right? Not always. For example, if you have carbon dioxide, right? Carbon dioxide has polar bonds. Here is a polar bond, and here's another polar bond. But what happens with these polar bonds? They cancel out. The overall molecule is non-polar, right? A molecule that has polar bonds will always be polar. No, unless the polarities cancel out. False. Good. Draw the illustrated carbon dioxide. Yeah, that's exactly the same example I was mentioning. Lone pairs make a molecule polar. Actually, no, because also the lone pairs can also cancel out, right? Because remember, depending, for example, in that case of krypton tetrafluoride, uh, they can do that. See that example. Example I was having, the two lone pairs of electrons, they are opposite, so they will cancel out. Okay, so these are the images for the same images I was having, and that the right, for the geometry. So I would recommend you to have that near you at all times, so you know what are the angles, you know what is the geometry. That's exactly the same thing. This is in the book, so you can either print this out or make a copy from the book. Okay, so please let me know if you guys have more questions regarding that chapter. You can ask me through the office hours, or also please watch the solve problem videos I will be recording shortly.